It's still going live. Okay. Good morning, everyone. Today is welcome to the Faculty of Engineering and Technology Seminar Series number 12. Today we have a talk by Professor Pradeep Kumar Sahu, and the title of his talk is Exergo Economic Analysis and Optimization of a Cogeneration System Using Evolutionary Programming. And today is the first time that we are going live online, and we have 7 people online, plus the rest of us here, or live, or actually in the seminar room. Okay, please join us. Yeah. Okay, so to introduce to you Professor Pradeep Kumar Sahu. He's from my department, Mechanical Energy and Industrial Engineering, and he specializes in thermofluids. Professor Sahu received a Bachelor of Science in Mechanical Engineering from College of Engineering, Bhubaneswar, India, and his Master of Technology from Indian Institute of Technology in Varanasi, and also PhD in cryogenics, yeah, from Indian Institute of Technology. Before joining the academics, he served as a research engineer in Superior Air Products Limited. His area of interest are exergo-economics, safety analysis of nuclear reactors, refrigeration and air conditioning, use of solar energy and other low-grade energy for air conditioning, ground source heat pumping, cooling and heating load optimization. He has guided 9 PhD students and 9 PhDs and more than 20 master's students. He has more than 45 international journal publications and similar number for conference papers. He has widely traveled countries like USA, Japan, UK, Czech Republic, Turkey, UAE, Kuwait, China, Mauritius, and South Africa to attend different international conferences. Without further ado, let's welcome Professor Pradeep Sahu. Welcome.
Is it fine from this place?
Yeah.
So this topic is exergo-economic analysis and optimization of thermal system. So I'll split this lecture into 2 parts. The first part will be the fundamentals of exergo-economics, or sometimes people call it thermoeconomics. Okay, all mechanical engineering students do read thermodynamics. Okay, so without that, we don't get a degree. But the essence of how we can use thermodynamics and economics to optimize a thermal system. That's what is the topic, today's topic. So that exergy, basically it is a combination of 2 words, exergy plus economics, that gives you exergo-economics, or some people call this is thermoeconomics, thermodynamics plus economics, thermoeconomics. These 2 terms are interchangeably used. Okay, so first I'll give a brief introduction. What is this and what exactly we are looking for? So if you look at as engineers involved in the analysis and evaluation of thermal system want to know what they want to know. Where do the thermodynamic inefficiencies in a system occurs? How high they are, and what causes them? Basically, if you are looking at a thermodynamic system, if I want to optimize it, minimize my losses, then I must understand what are the thermodynamic inefficiencies, how much they are, and where this. What is the cause? Basically, this. The second point. Once I know that, what measures should improve the efficiency of the overall thermal system? Then, how much do the thermodynamic inefficiencies cost to the system operator? Okay, so obviously we must, can we quantify that? What is the losses in terms of money? what we are, the operator has to pay for this inefficiencies. Then what measures should improve the cost effectiveness of the overall system? Now the last point is, it is not only the efficiency, I'm saying cost effective. Suppose if you are producing a product, am I reducing the unit cost? Suppose I am producing cooling or electricity. Objective is we must reduce the cost per unit. That has to be minimized. So, an energy, normally most people go for fast analysis based on the first law of thermodynamics, which we call this an energy-based thermodynamic analysis. Here what happens, it identifies only the energy transfer to the environment as thermodynamic inefficiencies. So whatever energy you are losing to the surrounding, that is treated as only is the thermodynamic inefficiency. Okay, I will clarify these things later on. Fails to identify any inefficiency in an adiabatic process. Normally, many times we come across in a throttling process, throttling valve, which we call the isenthalpic process. Enthalpy remains constant. If you have a throttling valve, inlet enthalpy, exit enthalpy remains same. If I'm analyzing based on first law, I'm not losing anything. But that's not true. The reason, throttling process is a irreversible process. You cannot reverse it. You cannot go back to the initial state. So first law doesn't recognize that one when you are analyzing based on first law. Misleads the engineer by considering as an inefficiency the heat rejection to the environment dictated by the second law of thermodynamics. You know that the Carnot cycle is the most efficient engine one can imagine. Yes or no? But still, a Carnot engine, if you take QH, you have to reject some and heat to the surrounding. Yes or no? Without that, you cannot operate a cycle. But as per first law, whatever heat you are rejecting, that is a loss. But if I look at from the second law point of view, that's not a loss. We'll come back again to that one. Okay, so if you look at it, it's a very simple diagram of the Carnot cycle. So what we're saying, we have a source at TH, then the engine which is taking QH, always we have to reject some to the temperature, and we are saying this TL is the environment temperature. Generally, the heat is rejected to the environment. It's not any other temperature. The environment could, if it is air, it is air temperature. If you are using water, it will be water temperature. Okay, so but this is the maximum I can produce, and how much it will be rejected is dictated by the Carnot efficiency, which depends on the temperature TH and TL only. Yes or no? How much you can, if I know, suppose if it is 400, suppose it is 1000, this is 300, then only 70%, whatever heat I give, only 70% I can convert, we can convert to what? The 30% has to be rejected. So that 30%, as per first law analysis, is a loss. But as per second law, it is not a loss. You cannot gain that way. You don't have any way to recover that way. Okay. So when you define the exergy, this things will be clear. So hence, there is a need for a additional concept. Okay. So what is that concept? This concept is exergy. Okay. Exergy, or in thermodynamics books, you will find this is called availability. Okay. Either some old books you will find they say availability, but newer books, if you are referring to the new, this is exergy. Okay, so what is exergy? Is the maximum theoretical useful work obtainable from a thermal system as it is brought into thermodynamic equilibrium with the environment while interacting with the environment only. Okay, so while you are, if I have anything at a temperature, any temperature, it could be higher or lower temperature, it has a potential to produce work. Okay, If it has a higher temperature, you can run a Carnot engine using the high temperature and the environment. If you have a low temperature, still you can run a Carnot engine. The environment will be high temperature, the low temperature is the low temperature, TA. Environment will be TH. Still you can run a Carnot engine. So, or you can run an engine. So, any deviation from the atmospheric or the environment conditions, we have to pay for that. You cannot achieve that one without paying anything for that. Okay, so represents the useful part of energy of the process operating above the ambient temperature. It says above ambient or it could be below the ambient. So basically represents the useful part of energy process processes operating above the ambient. So I'll go back to my previous diagram. So now if I say this is TH is 1000, this is 300, assuming the room temperature environment is 27 degree, this is 1000 K. What is the, if I am taking 1000, again I say, if I am taking 1000 or 100 kilowatt QH, only 70 kilowatt I will get as useful work. Okay, 30 has to be always lost to the surrounding, which is dictated by the Carnot efficiency. So basically, when that 100 kilowatt is available as 1000 Kelvin, my exergy is 700. Okay. If I say this one is available at same 100 kilowatt at 500 K. Okay. So what is our efficiency now? 40%. You see, I have same amount of energy. One was at 1000 K, the second one is at 500 K. But how much I can produce? In one case, I can produce 700 kilowatt. The second case, I can only produce 400 kilowatt. So if I am comparing, suppose, same engine which is operating at two different temperatures, then their efficiencies are not same. So basically, the source will decide what is the work potential of that one. Okay. So that's why we say what is the maximum useful. Then a real engine should be compared with that potential. If I am operating a real engine between 1000 and 300, then I will compare how much of work suppose I am getting. If I am getting 600, I will not say that based on the second law, I'll compare that 600 with 700. Out of 700, I am getting 600. If I am operating the engine at say 500 and 300, then I will say whatever output I get, I will compare that output with 400. Because 400 was the availability of the exergy of the stream when it is at 500. So basically is a major quality of the energy. First law never assigns an attribute to quality. Basically, higher the temperature, higher is the quality of the energy. Okay. So if you say the energy is available at 2000 K, definitely it has more work potential than that is available. When it comes to the environment, if whatever energy is available at the environment, it has zero potential or the quality is zero. Because when I put in the Carnot, both the temperatures are same. What is the Carnot efficiency? Zero. So that's why the second law always gives basically the measure of the quality of the energy. So one has to understand that. Then when I am doing a exergy based, I can identify what is the location, the magnitude, and the cause. All the three things of the thermal efficiency in a thermal system. A detailed analysis, exergy analysis will show us how much inefficiencies in particular components is occurring, and what is, then you can, from thermodynamics, you can know what is the cause. Okay. Then calculate the real inefficiencies which are exergy destruction. Basically, unlike energy, exergy is not conserved, it is destroyed. Okay, so exergy is destroyed. So you can say calculate the real inefficiencies which are exergy destruction within the system and exergy loss. Basically, this is loss exergy transfer to the environment. If suppose environment is at 300K, if you are suppose from the flue, you must have seen that from the power plant we have chimneys and we are rejecting heat to the flue gas goes up. So that is at a higher temperature. So when you are disposing anything at a higher temperature, you are losing something. That is loss. Okay, because that energy has some work potential, but there are certain constraint. You cannot cool this flue gas below certain the dew point of the combustion product. Okay, so because of that, certain things has to be maintained. Then very simple analysis. We are saying if you are suppose normally when you go for the analysis, we subdivide the system into smaller components. Okay, so if I am looking at any component, so if you look at that, I have a component, I have a element E in, that E stands for exergy, and giving certain input which I call fuel. This is not exactly a fuel which we fill. It is the energy which we are supplying to get a. Suppose if you are putting electrical energy to get our cooling, so that is my fuel. Electrical energy which I am supplying to the system, that's my fuel. So we have a component, we have a product. So here what is happening is there could be some losses. If you are losing heat to the surrounding, then that is a loss. Then ED, I'm saying that is exergy destruction. This is the loss because inside the system. Because you can see wherever you have a process, there could be thermodynamic irreversibilities and some natural processes. Means if I suppose you have a piston cylinder arrangement, there will be always frictional losses. So these internal losses we call exergy destruction. Then always each component has a desired output that we call product. Okay, so basically for the purpose of analysis, we will decompose the system into subsystems, and for each systems we will define what is the fuel or what is the incoming energy we are taking into it, what is the output of that, what is the desired output from that subcomponent. Okay, and if you look at that, this out will be in minus this minus the losses, destruction minus loss. Okay. But normally what happens in any particular system, I would like that my output has to be a constant. Yes or no? If you have a power plant, you would say, okay, we should produce 1000 megawatt, or even if you have smaller things, if you have air conditioner, you'll say, okay, I need 1 ton of cooling, which is equivalent to about 3.5 kilowatt of cooling. So that is a desired one. So how I can reduce this is fixed. If we can reduce this destruction and losses, then my input requirement will be low. Okay, but normally what happens, if you want to reduce the losses and destruction, we will go for a better system. Yes or no? The efficiencies has to be higher. But the moment you go for a system which is more efficient, you will pay more. Yes or no? It is not free. So you have to pay more for that. Or initial investment has to be more. So as an engineer, we have to see what configuration will give us the lowest product cost. Okay, that's the objective. So basically, okay, this is the thermodynamic relation for to calculate the exergy rate of exergy is okay. These are the, if you know the state, one knows the state point, you can calculate the exergy associated with the system. Okay, so then when I'm going for exergy based analysis, certain things we would like to calculate. What are those? So assuming there are number of components, if you are looking at the kth component, what is the exergy destruction in the same component? Then exergy loss. Then what is the exergetic efficiency? When I say the exergetic efficiency means, I'll say what was the useful energy I had given to this system and how much of that is really converted to product. So that is our exergy. This is not the energy. This is our exergy which we calculate using that formula. Okay. Then this is the exergy destruction ratio. We can always calculate what is the total exergy destruction in the system. Okay. Then I know individual subcomponent how much it is occurring. Okay. So that exactly gives me how much exergy destruction is taking place in individual components. So once that's the two ways we can say. Either it can be given as a percentage or it can be given in a total. I'll show you the calculations when you look at these things. Then we have to link that with economics. Whatever thermodynamic analysis we have, because what I am saying, if you want to improve the system performance, your efficiency will go up. With that, the price also goes up. Okay. So what are the relationship basically? Exergy is the only rational basis for assigning monetary values to interaction that a thermal system experiences with surroundings and to the sources of thermodynamic inefficiency. We'll say that suppose what is the unit cost you are giving? Suppose total cost is, this is the my exergy. So I'll give a some cost to my system. Okay. Suppose if it is a coal-fired power plant, so I say fuel is my coal. So what is the one cost of 1 kilojoule of coal? If you convert their calorific value and what is the cost, so I can always say these things can be calculated. So if you have suppose a cooling system, your input is electrical energy. I know what is the unit cost of the, so that small Cj is the cost of the unit exergy or the unit energy which is going into the system. Okay. These are the average cost for a unit of exergy. So you have to basically write equations. Okay. The real cost sources in a thermal systems are basically cost of the fuel and other materials externally supplied to the overall system. Any material we are supplying, those things we know what will be the cost. Okay. So the second thing is the capital investment for each component. Then operating and maintenance expenses. Then this is the one we have to calculate. What is the cost exergy destruction within? Because we are saying all the systems are irreversible in nature. So how much cost we are paying because of those losses, thermodynamic losses. Okay. Then exergy losses from the overall system, how much that goes to the surrounding. Then okay. The evaluation of the system components from the exergy means you have to calculate all this information. Exergy based variables, exergy loss, exergetic efficiency, or the ratios, then cost of exergy destruction and cost. When I go for this kind of analysis, the biggest uncertainty, the thermodynamic part we can take care, but biggest uncertainty comes here, the cost of the component. And that too, linking that cost with the efficiency. So that will be a source of uncertainty. Then the sum of these two costs determines the economic importance of the. So when you add these two, this one and cost of exergy destruction, capital investment cost plus cost of exergy destruction will say which component is more important or which should be attended for first to improve the overall system. Basically, we'll take the sum of cost of the exergy destruction, cost of the capital investment. Whichever component has highest value for this, that is the most important component in the system. because that is most expensive, not only from one, we are combining both. Then when you plot this one, probably we'll find, okay, if you look at, as the efficiency increases, the capital investment will increase. But simultaneously, the cost of exergy destruction will reduce. But when you combine, probably we will reach the point somewhere here. So this will be probably the region where the system should operate. So that is a, yes.
Can I ask questions? Sir?
Yes, yes.
Okay. So the optimal efficiency, why is it not at the point whereby the CD, why are you not considering what I will call the...
No, you are taking the sum. Where the sum is minimum, we are taking. It has the sum has to be the minimum. But you are saying why not here?
No, I mean why not relate that equilibrium point, the intersection point?
Okay, I have given a range. Okay, we have given suppose if you say why is a range? Normally, if you are looking at the prices and other things, is not a fixed parameter. They will vary with time. Okay, and if you look at particularly energy prices will go up. Given a choice, I will always go to the right side. Instead of left, I will opt for a system which has more efficient, and maybe it will cost little bit more. Maybe if you go for a say kind of a sensitivity analysis, that will give you a better idea where you have to fix it. If you take your cost, increase the fuel cost, then reanalyze, you'll reach probably. My preference will be I will opt to the right side. Okay. Otherwise, you can always have a minimum. You can say that's the exact minimum. But when you are designing a thermal, this is theoretical analysis. But then when you go for procurement or things like that, you may not find suppose you want to buy a compressor. Your calculation says the efficiency has to be 92%. When you are in the market, you may not find a compressor which is 92%, it is 90%. Okay, so that you are analyzing, you are not manufacturing or those things like that. So you have to select the best of the equipment available to match your requirement. Okay, then the other thing is the second link between the thermodynamics economics. Okay. The cost per unit exergy destruction is different for each component and depends on the relative position of the component within the thermal system. So if you have a complex system, I have 10 components, the cost of a unit exergy is not same for each of the components. That I'll show you with a simple example. Now suppose we have this is a very simple example. We have 3 components. Okay, I'm assuming that component 1, 2, 3, and we're assuming in each component the exergy destruction is 10 units. Okay, this is a simple assumption so that our life is easy. And assuming my input is here is 100 units exergy. So how much I am producing here? 90. Then I'll be producing here 80. Then it is 70. So assuming my unit cost, okay, I have calculated in Indian rupees or whatever you can use this one. So my cost is here I am putting, and here I am assuming that already we have the system, the cost of the equipment is 0 now. We are not taking the cost. When you add that, this will again reduce. Okay. So assuming that the cost is 0 and getting 90 units. So what is my cost now? My input was 100. I'm getting 90. So now the unit cost is 1.11 here. Unit cost of the exergy. Because here my 10 units which I'm losing, that will be at this rate. It is not 1. If I'm losing it here, when the unit cost here is 1.25, and when I go out here, the unit cost is 1.43. I have not taken into capital investment cost. Okay, so the cost of exergy at each as you go further down the system, you'll see the cost is increasing. The final product will always have more one. Okay, so I think it's clear.
Okay.
Sir,
Yes.
if I'm sorry,
No. I can take the question. I'm not a student who is disturbed.
Okay,
Okay.
it's okay. It's okay.
Okay.
Let Professor Sao finish. Then we'll
No, you can
take
ask.
questions.
No
Okay.
problem.
okay, if I understand how you are determining this cost now, you are comparing the energy from E2 relative to E1.
Not energy. This is
Okay,
exergy.
Exergy, sorry.
Exergy.
Exergy.
Exergy is basically the maximum work potential of a given system. Okay. Or
So, like C1 will be E1 over E1. C2 will be
Yeah.
E1 over E2, if I'm correct, sir.
okay.
If I'm correct.
Yeah.
So, C3 will be E1 over E3.
E.
E1 over E3. Is that how you estimate the cost? C3.
Yeah. Basically, you are moving in that way.
Okay.
But if I have to calculate the exergy destruction, my unit here, I'll take the unit cost is here. If I have to calculate my exergy destruction, cost of exergy destruction here, I'll take the unit cost this one. Some people take the average of these two also. Okay, so it depends what kind of assumptions one goes with. Okay. Basically, when you have a application where one can most important things one can go for the design and optimization. But if I have a run system, you can always look at the operation optimization or diagnostic applications. In these things, what we do basically can say, when you look at the optimization, okay, optimization definition is very long. A truly optimized system is one for which the magnitude of every significant thermodynamic inefficiency is justified by considerations related to cost or is imposed by the boundary conditions associated with available material, financial resources, protection of the environment, government regulations together with safety, operability, reliability, availability and maintainability of the systems. Okay, that's a big one, but okay. Optimization, here we are not given any say that if you look at that financial environment protection, other things are not taken into account obviously. Only we are looking at thermodynamic and cost for the optimization. Okay. Then operation optimization, basically, if you are looking at we can say capital investment represents on cost. Means if there is no already you have a system, then in the analysis I will eliminate the capital investment. Only just calculate the exergy destruction cost, like that. How much exergy is being destroyed, that will help us to understand how the system is performing. For diagnostic purpose also, you can always calculate the exergy destructions, all those things. Then you can compare what the initial claim was there from the manufacturer. Is it matching that one or not? Okay. Then the second part of my talk is basically the application of this one to a cogeneration system. Here we are assuming that, okay, cogeneration systems are typically in-house. Many plants, they prefer to have a cogeneration system where they need both say electrical energy as well as steam. Okay, so we're assuming that it produces 50 megawatt of power and 20 kg of saturated steam at 2.5 bar. Typically, some process industry that need this kind of. So then if you look at this one gives me a simple model. I have taken this one, and we're saying then we are taking, this is a first one, we have a gas turbine followed by a steam turbine, and part of it we are producing some saturated steam here and power. This is, and your objective is you are producing this. These are the set points, and this 15 plus 17 is the we're producing some power here, some net power here. So these two sum will be 50 megawatt, and this is one. So with these assumptions, this problem was solved. But I'm not going to much detail. Just most likely I'll skip those things. Say, okay, these are the initially. Basically, you have to consider a base case data based on your say conceptualization or what you perceive the system is. So we are taking consider the base operating temperatures, efficiency of the components. Those are the major components. Because here if you look at, we have divided this into say 8 subcomponents. So based on that, you have to find what are the parameters for each of the case. Then there are certain, when you do go for analysis, we definitely have to go for some assumptions which should be realistic. Okay, so basically the cogeneration system operates at a steady state. Ideal gas mixture principles apply for the air and combustion products. Heat loss from the combustion chamber is 2%. Basically, this is a typical say assumptions, and pressure losses has been assumed something. So based on that, I'll go back to. So once you assume those things, then you can calculate the properties. Okay. So now what I'm saying is, this table says the state properties and exergy of the each system. This is a simple thermodynamics. You can calculate it. Okay. So next step I will say. Then we have defined what is my fuels and what is the product, what I am getting from each of the sub-components. Okay. And what is the overall system. So because we are saying each component must have a fuel, must have a product. Okay. So those are the things defined. Those were really, if you are interested, you can say it takes much longer time to understand these things. Okay. So now I'm coming back to this one. Okay. So each of the component, now we have calculated what is the exergy destruction in exergy destruction and exergy loss. Then if I look at the ratios, this is basically, this one says what is the component wise loss. This one gives percentage loss. If you look at this one, the total loss is 42.4, whereas the single component combustion chamber contributes 28 points. I was saying we will know what is the how much irreversibility is taking place per component and what causes. Then you can always see these are the magnitude is this one. Percentage wise, you can say one can calculate what fraction of that total destruction is taking in a particular. So obviously, if you look at this is the one where maximum amount of exergy destruction is taking place. So then we'll okay. Then, but here I cannot say this is the one component I have to take into account. I have to improve this one first. Means in certain components, probably as an engineer, you cannot do anything. But the next one is we can go for the exergy costing exergy streams. So from that, okay, we'll I'm just skipping these things. Okay, so I'll get I was saying that each component, what is exergy, cost of exergy destruction, cost of exergy loss, capital investment. Okay, then the total cost. So I was saying when you combine this, the component having the maximum value of this one. So this is the most important component you have to attend first. Okay, then what is the next one? So next one is probably the heat recovery steam generator. So that is the component one has to, if you want to improve the system. Yes.
3 minutes.
3 minutes. So basically that's how one has to look. Okay. So, okay, I'll just, when you look at that, when I'm looking for optimization, I have my objective is increase in exergetic efficiency, decrease in product cost. Okay. So if you look at it, has both has to be satisfied. So, but when I say, and I'm increasing the efficiency, the cost of the things. So how do I formulate my optimization problem. Okay, so my optimization problem is, okay, if this is my cost of the components, but when I increase the efficiency, definitely the cost of exergy destruction and losses will be minimum. Yes or no? If the efficiency is increasing, the destruction cost, so I'm taking as the cost of the capital investment, cost of the exergy destruction and exergy loss. So if I combine that as my function, I can formulate a minimization problem. Minimize this. Because otherwise it was conflicting requirements. It sounds conflicting, but with this one, we have reduced it to a minimization problem. Okay, so using that, have we used evolutionary programming for solving this one? Okay, it itself is a topic. It will take a lot of time, so I'm not going to discuss this one. So after this, these are the simulation results. Okay, and based on this, what we found is our base case. Then after optimization, we got these are the parameters one has to. When I say we have got this theoretical, but if you are looking at compressor efficiency, you might not get at 81.5 or something like that. But you have to choose something which is close to the optimized parameters. Okay. Then the last one, it says the comparative results of optimum and the base case. We have the base case, the optimum case, and what is the variation it says. The total investment cost has increased by 7%, but electrical efficiency, if you look at here, both this electrical efficiency and thermal efficiency has increased. But when I had calculated the payback period was about 3 years. So with this, if I say if I'm getting back the additional investment can be recovered in 3 years, this is a very good investment. Okay. So, okay, this there are other things one can do, always distinguish between avoidable and unavoidable exergy destruction and things like that. Then, okay, consider the interaction among the system components. There is another way of looking at how one can optimize these things. And okay, this is with this I am finishing. This is one of my paper which was published in Applied Thermal Engineering. So anybody wants it, if you are really interested, this one. And apart from that, maybe I have another 7-8 papers related to thermoeconomics or exergoeconomics. If anybody is really interested, you can get those papers from me. Thank you.
Thank you very much, everyone. And this is just to remind us all that we are live online. And so our setup will be, if you want to ask questions, please come forward so that the persons online can also see you and can hear you properly because the microphone is here. Okay, but I would like to first recognize that Professor Suglu was here, the Dean for Faculty of Engineering and Technology. Okay, we are open now for more questions. Professor Itayo, do you have further questions to add from your previous question? Please, when you ask question, come forward so we can hear you from the microphone.
Okay, any questions? Yes.
Come on.
I will start.
Yeah, please accommodate our audience online. There are 6 of them.
So you spoke of subsystems and that the cost, I assume it's safe to say the cost keeps increasing as you go towards the product.
Yes.
From the initial.
Yeah.
I would therefore suggest that instead of saying the cost is not equal, you should say something like the cost keeps increasing.
Yeah.
Yeah.
Cost will go on increase. It means the final product will be always, suppose in a cogeneration system, suppose you have a cogeneration system, you are producing both steam and electricity, you want to sell it.
Yeah.
So what is the price of steam and what is the price of electricity? How do you determine? If you do a proper analysis, probably you will arrive at but If you say, if I analyze and if the cost of steam is coming higher than electricity, or if you charge steam cost is more than electricity, that's not acceptable. Okay.
Well, the equation that you wrote, it says that it just shows that they're not equal, you know. But
Yeah.
I was thinking that you should just say it keeps increasing.
Keeps increasing.
Yeah.
They're not, I said they're not same, but normally somebody will assume, okay, whatever input I had given at the initial, that is the cost of exergy destruction. When I calculate exergy destruction, that initial cost I will not take.
Yeah.
It will be different, because when I produce something from a component, I have not considered there the capital investment. So add on the capital investment, you will see the cost will be more. Go on increasing.
Any other questions?
Yes.
Okay, I have a question, Professor Sahu.
Yes.
Yeah. My question is exergy a word that you coined yourself?
No, no.
Or is it already existing?
Oh, this is universally existing.
Oh, okay. Yeah, it's new to me.
This exergy, okay.
Yeah.
Probably in your days, if you have read the thermodynamics, the term, have you had the term availability?
Yes, availability. Yeah.
The same one is the
Okay.
exergy. Okay, but availability, exergy, it's more specific. It says anything you have, if you bring it to the environment while interacting with the environment. So how much work you can produce?
Okay.
That is the work potential.
Okay.
So that work potential
Work
is called
potential,
exergy.
yeah. So Professor Sahu, my follow-up question is that if it's related, is exergy related to energy itself? And if it's related, how are they related in terms of equation? Is it just a proportionality constant, or is it a
Even
linear
the
relationship, or no? No?
Basically, exergy is a function of environment temperature. What is your environment temperature? Okay, so if I go back, so okay, I'll just maybe somewhere. So in the beginning, somewhere I've written that. Oh, this one. So if you look at, so basically this is a function of your, this is the given state, H and S, enthalpy and entropy. This is the enthalpy and entropy of the environment. This is your environment temperature.
Okay.
So this is a function of the environment temperature. So if you are, suppose you have some anything, suppose you have, again I say, take the same example, some energy is available at say 1000 K. My environment is 40 degree, I get some exergy. If my environment reduces to 0 degree, my exergy potential increases.
Yes.
So it's a function of our environment and the given state of the matter.
So it is. So what you are saying, Professor Sahu, is that it is different from the conventional way that we know energy is.
Yes.
Okay.
But
is there a relationship?
this is the link you can use. Basically, this is the relation, because this one gives you the energy. Enthalpy is what? That's our energy. Internal energy plus PV.
Okay.
Okay. So, but exergy is truly the actual work potential when you bring a substance from any state to the state of environment. That is the actual work potential. Suppose the environment has so much of energy. Can I use that one? Basically, you just think of, can I run a Carnot engine?
Because my question really, Professor Sahu, leads to the point of I'm leading towards a question of why is it not enough to consider energy potential? Why do we need to have something exergy to consider when what is missing if we consider only energy?
Okay.
Yeah,
I have given the examples while I was talking. If you look at a throttling process, what is the throttling process? If you apply the first law, you get initial enthalpy. The final enthalpy is same as the initial enthalpy. Isenthalpic process means your energy is not changing. but the quality of energy is changing because the work potential after the expansion valve is low. First law does not recognize that. If I have a suppose steam at say 40 bar and 400 degree, you reduce that to, in an isenthalpic process, you reduce it to say 10 bar and say 27 degree. The work potential is zero. The work potential is not zero. If you reduce it to 1 bar and 27 degree, you can do a isenthalpic expansion process, come back, then you arrive at that one, say room temperature, the environment condition. Then the second stage, the work potential is zero. But first law doesn't recognize. As per first law, it will say it has same enthalpy. Or means if you go
Because there's no actual energy output.
energy is the same.
Yes, I mean there's no actual.
But you cannot produce any useful work from
Yes,
that.
yes.
So
Yeah,
that
no
is the
change in
degradation.
energy.
So basically, the second law is associated with the quality of energy. First law does not distinguish whether heat is available, any energy is available at say 1000 K or 500 K. If same energy is available at 1000 K, we can produce more work than it is available at say 500 Kelvin. When it is at 1000, your Carnot efficiency is 70%. You can convert 70% of your use given energy to work. But when it is at 500 degree, your efficiency is 40%. So only 40% of that can be converted to, that is theoretical maximum. So that quality is associated with the second law, not with the first law. First law analysis does not recognize these terms.
Any other questions?
Yes.
So there were 2 or 3 components that took a lot of loss in terms of exergy. So how do you solve it? After you calculated that these components cost a lot,
Okay.
how do you solve it? How do you take it out?
No, then okay. Each individual component, as an engineer, you know how much you can do. You can, okay, analysis shows this is the component which is losing maximum, and then definitely that's the component you have to target first. Then you have to, within your limitations, you have to improve that. Okay, that's the way it has to be done. Because suppose if you say your heat exchangers, so that heat recovery steam generators, okay, there you can probably think that we can increase the area and something we can, so that you can increase the efficiency or something. But combustion chamber is such a system, you cannot do much with that. Okay, probably you can consider what will be the different kind of, okay, probably the combustion process and other things. But certain things, you have to look at within your limitations. You have to improve it. Suppose in a electrical, suppose motors, the generators. Now, if you can think, you can increase the efficiency by 1%. That's a huge increase. Somewhere even 0.5%. If you are producing, you have a power plant 1000 megawatt. If you can improve 0.5%, then still it is a significant amount. So that's what you have to see, where and how much you can improve. And normally, if you are an engineer, you are assigned a job, you don't get a mandate that you can spend as much as you want. You'll be given a mandate, okay, this is your budget. Within that, you have to do whatever you can do. Okay.
We can take 2 more questions. I will prefer somebody who didn't ask a question. Are you tired?
Okay. Any more questions?
So, okay, one last question. Really, I've been really wanting to ask this. Why is it because why I mean, again, why exergy versus energy? Is it because you're doing economic analysis?
No, it's the
No?
quality. It's associated with the quality.
Well, I mean, energy also is associated with quality. If you say
No.
talk about efficiency, no, no, not enough.
Just like
you say not
that's,
enough.
that's not scientific. Even
But why is the power plants still looking at?
no. Okay. Just I see.
Okay.
If I go, I'll take you back to this.
I mean, why are the power plants considering energy efficiency instead of they say exergy efficiency or something like that?
Okay. If you look at that, if you can improve the exergy efficiency, the energy efficiency also increases.
Okay.
But you cannot assign a cost to energy scientifically in a rational manner. But I can always assign a cost to exergy in a scientific manner.
So it's
that's-
really about economics now.
Yes.
Counting the
So
cost.
yeah, costing.
Yeah.
You can
Yeah.
because now I am coming to this. Because if you have this one, the Carnot engine, which we say as a engineer, we say this is the most efficient engine. Yes or no? But when I am doing this one has to reject something to the surrounding. As per the first energy analysis, this is a loss. This loss. But exergy analysis does not consider this as a loss. This is not a loss.
It is a cost.
No, it doesn't it. The cost is here associated with what?
There's a destruction cost. This is a destruction cost now.
No, this is not an. As per first law, this is a loss. As per second law, this is not a. As per exergy analysis, this is not a loss because this has to go to the environment as per the constraints. So second law doesn't consider this as a loss because your Carnot engine has to reject some. It's technically it has to reject heat depending on this. What is this temperature? If this temperature is 1000, this is 30%. If this is 500, this loss is 60%. First, as per first law, but second law doesn't consider this as a loss. Second law, I compare. This is my work potential. How much I am getting out of this one? Always my comparison is this is the total possible one, and how much really we are getting in a real device. I'll compare with this one. Not consider this loss. Okay.
I would like to ask, how are the exergy costs different from the environment losses? I mean, in terms of the causes, what causes the environment losses, the QL, and what causes the exergy, the losses that the environment causes?
But anything when you are rejecting to the environment, if it is at environment temperature, the exergy potential is zero. It doesn't have any work potential. Suppose the environment has so much of energy, can I get anything out of it? Because it doesn't have a work potential. So that is the most important thing. So when you have the quality associated with a state, then only you get the work potential. As you go closer to the environment, so that's why many times you do low-grade energy, use of low-grade energy. What is the meaning of low-grade energy? The energy which is available closer to the environment temperature. Okay. Many times we see, what is the low-grade energy? What is the meaning of low-grade? Why it is called a low-grade? Have you heard the term low-grade energy?
Low-grade energy.
Yes. Low-grade energy means the energy.
It's not a good quality.
No, means it is available at a temperature which is closer to the environment.
Oh, okay.
So that's why we are considering. Most of the time, you see the renewable energies. They're not very high-grade energy. They're solar energy. If you want to produce, say, hot water, you get something like how much temperature you can get from the solar energy? 70 degree, 80 degree. Otherwise, if you want higher, then you have to invest a lot more, go for concentric type of things. Okay.
I'm trying to ask if anybody from the audience would want to ask questions.
Okay. So
It's automatic that there will be
yeah,
environment losses.
when I put what is the high temperature basically? If pH is closer to this one, this becomes bigger and bigger, your efficiency, your work potential, and when this TH equal to TO, this is 0. So that even though we have so much of energy with the environment, we cannot use it. The work potential is 0.
Okay, any more questions? I think it's a very informative discussion with Professor Sahu, and only we need to remind ourselves of the background on energy and lessons that we have long forgotten.
No, I was expecting some more master students and posters to be here.
But still, it's very informative for us, considering that there are many more areas that we can make useful information and useful research, especially towards, I guess, economic consideration of power generation.
Means it can be applied to all
It can
thermal
be applied to all other areas. Yeah. Okay. So we have one more last question.
Okay, let me just this exergy analysis, especially the economic aspects, how much of it can be applied maybe to analysis of energy utilization in manufacturing processes?
Okay, in manufacturing processes. Let me say, when you look at the manufacturing processes, okay, you have to look at each component. Even same way, you have to analyze how much energy you are consuming, what is the theoretical consumption, and what is the loss. So basically, always you have, for any manufacturing process, you know what will be, always there will be a theoretical one, and what will be the actual loss. But there are certain difficulty with exergy analysis. For the exergy analysis, basically these are related with fluid, some is associated with some fluids and something like that, where you can calculate the thermophysical properties. Without thermophysical properties, basically when I'm using this, there are some other relationships. Okay, when I'm using this one, and in a thermal system, I know that I have fluids, which I know the state point temperature, pressure temperature information, from where I can calculate the state properties, then I can calculate. But if you have a process where I cannot calculate these things, then how can I apply this one? There is a difficulty. If you cannot calculate these things, then you cannot calculate, we cannot apply this one. Then you have to rely on energy analysis.
Okay. I think it's already time, and we have to finish the seminar. I thank you all for coming. And there's one question online regarding a published paper related to this presentation. Professor Sahu will be happy to share it to everyone, and you can just contact him through email. It's Sahu P, yeah? SAHOOP @bus.ac.bw.
In addition to that, I have other papers also.
Yes, Professor Sahu is a full professor from Mechanical Engineering Department, and he has a lot of research work in many other areas besides this power. Also, mostly thermoeconomics. Yeah.
No, not mostly.
It's a fraction. Yeah. A minimal fraction of your research.
Maybe 7-8 papers you can.
Okay. Please do check Professor Sahu online, and also feel free to contact him via email. And again, we thank Professor Sahu, and let's give him a big round. Thank you.
Thank you.